Good morning, good afternoon, and good evening. It's truly my pleasure to give this Rilem Rock and Talk seminar. And in this seminar, I'm going to talk about artificial intelligence and machine learning for cementitious systems. I'm Anoop Krishnan from Indian Institute of Technology, Delhi. What is artificial intelligence? The simplest definition of artificial intelligence could be to enable machines to perform tasks that humans could. So, does this mean that the tasks performed by AI is better than how humans are performed or better than how average humans are performed? This is very difficult to say. But one of the earlier tests for artificial intelligence was as follows. So, it's called Turing test, wherein you keep essentially a computer or a human behind a curtain, and the only way to interact with this person is through some sort of a screen that gives you the output to the response that to the question or the response that you give. And the example is this. One of this earlier experiment was this, that you have a conversation and you only have the text of the conversation. So there is a young woman who is asking the other person named Eliza, men are all alike. And Eliza asks, in what way? They are always bugging us about something specific or the other. Eliza, can you think of a specific example? Well, my boyfriend made me come here. Your boyfriend made you come here? So you have a conversation like this. Now, can any of you guess if either of this is a computer or a human? The interesting thing is that the young woman is actually a human and Eliza was a computer. This was one of the earliest chatbots that were created in 1966. This is Eliza by Weizenbaum, the first computer dialogue system based on keyword matching. So you can see that from this conversation, it's not very obvious that the other side is whether a computer or a human being, and thus we can say that Eliza has passed the Turing test. And the reason why I show this is also to tell you that the field of artificial intelligence is not new. It has not come in the last decade. It has been going on, and a continuous effort has been happening from 1966, although with some breaks in the middle. And what are the application areas? It could be natural language processing, like ChatGPT is used in almost all domains now, robotics, computer vision, automated reasoning, knowledge extraction, etc. What is machine learning? Machine learning is a subset of artificial intelligence, and this primarily represents almost all data-driven methods, right? So what it does is it uses available data to identify hidden patterns and learn progressively by self-correction. So the capabilities include clustering. That means, if you have people of similar kind, similar taste, can you group them? This is called clustering. In our parlance of cement chemistry, do you have materials or supplementary cementitious materials having similar behavior that enables improved strength or reduced carbon emission, or properties of, or early strength, etc. So properties of our interest. This is the idea of clustering, or essentially grouping things. Regression is to regress, in other words, to fit a curve. And this could be extremely non-linear, it could be linear, it could be for compressive strength prediction after 28 days, it could be for predicting things like viscosity, it could be for reactivity, etc. And dimensionality reduction is if you have input features that are related to each other, can you actually reduce the dimensionality? To give you a simple example, you have, let's say, calcium, silicon, and water, calcium silicate hydrate, right? So we know that the total should add up to 100%. So that means if you have calcium and silicon, then you don't necessarily need the H2O, because 100 minus Ca plus Si should give you the H2O, assuming that everything is represented that way. So in that case, although you have three features, you need only two dimension, and this is a very simple example of dimensionality reduction. But in many cases, we will have collinear features, and in these cases, you can reduce the dimensionality much more. Then you have property prediction and anomaly detection. And the important point is machine learning is essentially a statistical model, and data used for training should be proper, and it should be representative of the sample space. So if you don't have data, and if you're going beyond the data on which the machine learning model has been trained, of course there is no guarantee that your model will work well, and that's something that we have to keep in mind while using machine learning. So the outline of this talk with this background is going to be as follows. First, I'll give you a brief introduction into AI and introduction to machine learning, what are the different parametric and non-parametric methods, and primarily spend some time on one of the most popular methods named neural network. And then part 2, I'll talk about AI in cement and primarily focus on information extraction from literature, property prediction, and how to scale it up all the way to a cement plant scale, and how to use AI for accelerated cement manufacturing. So going towards the first part, a brief and quick and dirty introduction to machine learning. So if you have machine learning, there are 3 broad branches of machine learning that you can think of. The first one is supervised learning, the second one is unsupervised learning, and the third one is reinforcement learning. So supervised learning would mean that you have a completely labeled training data. In other words, you have composition and property. Let's say you have the cement composition and its strength. So this is a supervised training scheme wherein from the composition you want to predict the compressive strength, for instance. Right? So that's why all of this regression and classification will fall under this particular basket of supervised, and this is again one of the most commonly used machine learning methods. The simplest method is linear regression. Then you can have polynomial regression, support vector regression, random forest regression, neural network, and Gaussian process. I'm not going to explain these methods in detail, but just want to give you an overview that these methods belong to regression. Now, many of these methods used for regression can also be used for classification. So you can have random forest for classification, support vector for classification, and neural network for classification in addition to logistic regression. The primary difference between regression and classification is that in regression, you are regressing over a continuous space. For example, compressive strength can take any value, or cement emission can take any value, so it's a regression. Whereas in classification, you are grouping them into 2 classes. Let's say cement class 1, cement class 2, or let's say you have cement that gives improved earlier strength and cement quick setting cement, for example, and not quick setting cement, right? So these are basically categories, and you want to classify them into different categories, whereas in regression it's a continuous space. Unsupervised could be that you have some features but you don't have the output. For example, you have all the compositions of the feature cement, and you want to group them simply based on composition. You don't have any properties or any other attribute that you are using to group them, and this particular idea is called clustering, right? So you have some space and you want to group them, like in simple words, you have people of different ages, so you want to group old, middle-aged, and kind of young in some sense. So this means that you don't you simply look at the features of people and then from there try to group them, and that's the idea of clustering again. It is unsupervised because there is no output label against which you are trying to match. You are simply looking at the pattern and then grouping it. Reinforcement learning is a very interesting area where you teach computer how to let's say do something. Okay, so you might have learned about computer playing chess. So this is using reinforcement learning, wherein you allow computer to take an action and then give a feedback whether that action is good or not. Where would this be applicable in the context of cement manufacturing? For example, for online plant control, you want to always operate the plant in such a fashion that the emission is always below a certain percentage. So there you need reinforcement learning, right? So for example, you would always keep monitoring the emission, and suddenly if you see that the emission is going beyond a threshold, you would want to go back and control some process parameters so that the emission is brought down below this, and then you keep checking whether the emission has come down. If it has come down, this action is good. If it has not come down, this action is not good, and progressively computer will learn how to control, for example, a plant in an autonomous fashion, so that the criterion that we are interested in, which is cement quality and let's say emissions, are all kept in the desired range. So this is a brief idea of machine learning, and from this I go to the next step, which is how to choose the right machine learning model. The simplest idea is always start with the simplest model, right? Don't go for a complex model if your problem can be solved by a simple model. So if you have data set, first start with linear regression, and if it is accurate enough, just stop it there. If it's not accurate, look at how many samples do you have. If you have small number of samples, that's say for example 100 or 1000 samples, then go for methods like random forest or boosted trees, because these methods are really good for small data sets. But if you really have large number of data sets, and that's where neural networks start shining. So if you have 100,000 or a million data set, then go for neural network, because it will start learning patterns from the data. But if you have small data set, always go for random forest. A much more sophisticated scheme is given here. Okay, so I'm not going to go into the details of this. This is available if you are using this package called scikit-learn. This is available in the web page of scikit-learn. I have taken it directly from there, and the main point is to show that this same scheme that I have mentioned for regression could be applied for classification and for clustering, etc. So here you can see that if you have less than 50 samples, you should not be doing machine learning. Get more data first, right? Or maybe you should do linear regression and things like that, and don't go for any sophisticated machine learning models. That's what this means. And do you have labeled data? And if it is category, then go for classification. But if you are predicting a quantity, then go for regression. So that's why if you have less number of samples, again go for simple tree-based methods or things like that. And if you have more data, go for neural network, right? And same applies here in classification and in clustering. So this is just to give you an overview of what method to use when you're starting with machine learning. So let's start with the simplest machine learning method, which is linear regression. Maybe most of you know it, but I simply want to directly make a connect between linear regression and neural network, and that's why I'm talking about this. So here, let's take a simple example. So you have some property that you want to predict, which is given in the y-axis, and you have some feature, it's a one-dimensional feature. So that's given in the x-axis. And there is one data point here, which is, let's call it an outlier, because that's not following the trend of it. But the rest of this are more or less following a straight line. So you want to fit a line y equal to mx plus c to this. And how would you do this? You have the predicted values, which is given by mx plus c, or here beta naught minus xij beta j, and yi is the actual value. So you would minimize the residual sum of squares, or basically the predicted value minus the actual value, and then you would simply try to minimize this, and in that process you would get a straight line, right? And what do we mean by getting a straight line? We essentially mean we have to determine the parameters beta j and beta naught. That's all that you need to do. But when you have an outlier like this, when you try to minimize the error, you know that this outlier can have a significant influence, and this is addressed by something called regularization, which is a word that you would hear again a lot in machine learning. So in regularization, what happens is that instead of minimizing just the predicted value minus actual value, you would also try to minimize the weight. So think of it like this, that you are minimizing the actual and predicted value, and then you are also minimizing the beta j's, so that the beta j should not become a high value. So if you try to minimize both, for example, you will get, you will try to push this particular line down by minimizing beta j, but at the same time you are trying to fit on y predicted minus y actual. So you would get a very nice line like this, which is not too much high and exploded, and is still following the trend. So these are some simple machine learning techniques, and the reason why I wanted to give you an idea is, regularization is widely a word that's widely used in machine learning, but it's a very simple concept and it can be applied to linear regression as well. So when you train a model, what you would see is that, let's say you want to fit a straight line, right? And you would see with you have a horizontal, kind of line here. And then when you are trying to minimize the error, for example, here is the actual line. So you would first start with an x-axis. So this is a horizontal line. And then you want to minimize the error. In that process, you go along the gradient, and simply increase the slope of this until you get the best fit line. Okay, so this is the essential process of linear regression, but it's exactly the same algorithm that's used if you're using neural network or any other sophisticated methods, where you define an error and then try to minimize the error by going along the gradient. So you can see the slope is increasing by going along the gradient until it reaches the minima. So this is the basic idea of machine learning. Now there is this famous method called random forest. I spoke about this earlier as well. And in random forest, what you have is you basically group things into multiple categories and build multiple decision trees. Okay, so you start with a feature, then have a branch, go to this direction, and finally you have a leaf node, and the leaf node will have that predicted value. Again, I'm not going to go into the details of this, but I just wanted to give you an idea of what the algorithm looks like. Okay, neural networks, the most famous algorithm. Neural networks are essentially stacked linear regressions. Okay, so you have an input node, and then you have a hidden layer and output node. But what is each hidden layer unit? Each hidden layer unit is nothing but a straight line which takes input and then passes it as a linear regression. So for example, if you have one hidden layer unit, the output y is nothing but m1x1 plus m2x2 plus m3x3 plus c1, right? And this particular output comes out of each hidden layer unit, and that's why we call it a stacked linear regression. Then what is nonlinear about it? The nonlinear part of a neural network is the activation function, wherein each hidden layer unit, once you get the output y, is passed through something called an activation function, like for example 1 by 1 plus e raised to minus y. So you have a linear output, and that's passed through an equation like the one that I said, and that makes the whole thing nonlinear. And the example that I gave is a sigmoid function. The easiest way to imagine is, assume you have a switch, and you have switch on and off, and accordingly you will be able to fit multiple straight lines to a very, very complex curve. So you can have multiple hidden layers with large number of neurons, and you typically train this by splitting it into training and test data. Okay, so how is the training of artificial neural network? You start with dataset preparation, clean the dataset, impute missing data, remove outliers, etc. And then you make sure that your training data is representative of the major features of the data. Then you remove redundant variables, reduce the dimensionality, keep it as simple and minimum as possible. And then you identify the appropriate mathematical model depending on the size and nature of the data. Like I said, if you can do with linear regression, then do with that. But if you need a neural network, go for that. You need a random forest, go for that. Then you have to divide the data into training, validation, and testing. This is very, very important. So let's say, for example, if you have the whole data, divide 70% as training data set on which you train the model, and then you evaluate it on the validation data set. And if it's not good enough, you go back and then tweak the model, change the hyperparameters, have more neurons, change the activation function, change the learning rate, etc. And then test it until you're happy on the validation set. But the test set is the set that's kept completely hidden from this model, and once you have the final model, go and test it on the test set. But once you have the result on the test set, you should never go back and try to improve the model to get a better performance on test set, and that's exactly when you will have overfitting, etc. And the whole point is to see how general the model is. Okay, so with this introduction, we are now jumping to part 2, where we will talk about how this particular different techniques can be used in the cement literature. And you will see that what I have given you is a very basic introduction to machine learning, but if you think of how ChatGPT works or how complex models work, there are much more mathematical details, and you can get started with those. So let me start with a simple starting point, which is, let's say you want to extract information from literature. How do you go about that? This is an important aspect because if you want to do any machine learning, first what you need is data, and most of the data is hidden in the literature. And sometimes data is in the form of text, and sometimes the data is in the form of let's say tables and things like that. So here are some examples. quantitatively analysis of the effects of key factors on elastic modulus of UHPC is obtained using the proposed method. Okay, so this is not a complete sentence, but I've just taken a few sentences from literature. Carbonation of cement-based building materials is not only frequent trigger for corrosion of the reinforcement and things like that. So when you have sentences like this, what you want are some of the interesting features, like you want the property. So here elastic modulus is a property, corrosion is a property, materials, cement is a material, UHPC is a material, descriptors, powdered calcite. So powdered is how the calcite is, so it's a descriptor, right? And characterization method, X-ray diffraction is a characterization method, synthesis method or processing method, so that's carbonation. Then you have application, which is building material, reinforcement, etc. And then you have symmetry or face labels, which is gibbsite, kaolinite, thaumasite, etc. So the interesting thing is, when you train a language model, it can actually capture such very specific information from the sentences and give it out to you. So you have a complete information of the synthesis method, characterization, property, application, etc. from the literature. This is a powerful method that can be used with language models. So in this particular framework, what we have done is we have taken a lot of research papers on construction materials, and we developed a language model called SemScibert for cement by training it on a corpus of around 100,000 papers in cement, in the domain of cement and concrete. And then we have taken text and tables, and with tables for compositions we have extracted using a framework called Discomat, which we developed. And if you have tables with mineralogical compositions, we have extracted GPT-4. So you can now see how easily information can be extracted from literature. And using the method that I mentioned earlier, so you can see different materials extracted. You have CSH, mortar, cement, concrete, fly ash, Portland cement, etc. The frequency is written in the parentheses, and different applications, pavement, structures, masonry, building, and things like that. And if you look at symmetry and phase label, again you will see different symmetries and phase labels, and different synthesis methods include curing, carbonation, aging, hydration, etc. And if you look at information extraction, it's present both in tables and text, and it could be in cement chemistry notation or it could be in chemical composition notation, right? So here are two examples. So we used our framework and extracted both chemicals in cement chemistry notation and the usual chemical notation. So here is the extracted data that we were able to obtain. So we were actually able to obtain more than 20,000 compositions from the literature using this approach. So this includes C2S, C3A, C3S, etc. This is the cement chemistry notation, and this is the real notation where you have SiO2, CaO, Al2O3, Fe2O3, etc. And beyond that, you can have supplementary cementitious materials like fly ash, slag, fume, clays, and pumice, and all of those kind of things extracted from the literature. The other interesting thing that you can do is trend analysis. So for example, you can see how many, what is the kind of studies that have been happening in the literature. So you can see that after around 2009 or 2010, there has been an explosion in the studies on supplementary cementitious materials. Of course, there have been a general increase in the total number of studies, but specifically the field of supplementary cementitious materials have proportionally increased, and these kind of trends can be easily analyzed. So I will also suggest you to ignore the last data point, as we had taken data only up to 2023, and that's why there is a dip at the end, because we had collected only half the year data. So this is information extraction. Now you can also use it for images, right? So for example, microstructure segmentation. This is a simple picture, like microscopy picture of clinker, and you can see that there is A-light and B-light in it. And one of the common method used to categorize A-light and B-light is the point counting method as per ASTM, requiring counting almost 3,000 particles, right? And here it's very complex problem, because you will have non-uniform size and shape, and the colors can depend upon the etching process, lighting conditions, etc. So what did we do to address this problem? We manually annotated both A-light and B-light, and here is our training data set. We basically, so here when you have a microstructure, you have to actually manually annotate it. This is actually a tough process, and this is one of the most time consuming process in machine learning, developing the training data, right? And this also requires domain expertise, because you should know what is A light and what is B light, and if you don't know, this annotation will be wrong. So here you can see A light is around 1100 training data points and 173 test data points, and B light is around 764. And not just from this figure, we basically created around 200 such figures and developed the training data based on these 200 figures. So around 764 training data and 293 test data. And what did we do with this training data? We developed a model called Cementron. And Cementron is based on Facebook's method called Detectron, which uses basically a computer vision based architecture. So if you remember, I had mentioned briefly computer vision. Computer vision is the broad field where you uses images and some sort of machine learning models for image to identify patterns from image. So what it has is that it takes an input image, and then you have this backbone architecture that basically processes this input image and then passes it through several neural networks. Okay, and then finally what you have is you have a box mask which tells you which pixel is corresponding to which material, right? So the classification is happening at the pixel level, and you will have the number associate what material does this pixel belong to. Okay, so that's the essential idea, and then you already have the annotated number, so you try to minimize the error with respect to the annotation. So how does this perform? So we tried it both on grayscale images and RGB images. So you can see that the overall performance, the details of this architecture and the training data, everything is available in our paper called Cementron. This is already published. So if you look at the overall score, we are actually, the best model is able to give us 0.963. So that means 96% predictions of this models are correct. And it's also able to have good recall, which means out of all the B lights that are present, it's able to identify 87.6% B light, and in case of A light, it's able to identify 84.7, and the precision, which means out of all the predictions how many are correct, it's 96.3 for A light and 90.3 for B light. So it's on an average, this is very good prediction, because otherwise you would have to have a human sitting and annotating this and this is or counting this, and this is really expensive. So you are able to get almost with 90% accuracy each of these phases directly from this trained model. To really push the limit, we also took new data. That means this is from our own laboratory. We took an actual image that's not part of this original training data that was taken from literature. So this is under completely different conditions and in our own lab, right? And we annotated this. And here is this annotated A light and B light, which is the first column. And here is the predicted A light and B light. So you can see that the predictions are fairly close to the annotation, although for A light, for example, we see that a small part here is actually missing, but beyond that we see that the predictions are quite good and we are able to get almost 90% accuracy in terms of prediction. So what are the applications of this? It can be used for particle identification. So here you can see 1, 2, 3, 4. We can identify all these particles. You can do accelerated point counting. You can do particle size analysis, and for example, if you want to do some numerical modeling for maybe hydration or some multiphysics models, you can actually now automatically create this microstructure directly from the image that you have and use that for your simulations. So we now have a seamless pipeline starting from experimental data towards numerical simulation using this model, and this is just one example of how computer vision and AI can be useful for cement. So the last example that I want to talk to you about is how to scale it up to industrial scale. This is a project that we have been doing with the Global Cement and Concrete Research Network, and specifically Innovandi. And what we have tried to do is take 4 cement plants across the world in different parts of the world. You can see it's from South America, North America, India, and Europe, Italy in specific. And then took 2-year data, historic data, and tried to develop model for predicting cement quality, for predicting emissions, and all of these different important parameters. And this ties me back to the original story that I was talking about, reinforcement learning. Ultimate goal would be to have an online control system that enables a plant to operate by itself, ensuring that all the parameters and quality constraints and key performance indicators are satisfied. So here is a simple example of a plan. So you will see this, that you have a preheater tower, you have a rotary kiln and a clinker cooler. Preheater tower can have a kiln feed, and then there are several cyclone stages, and there are several process parameters associated with this, and then the hot meal goes inside, and then finally you have this clinker cooler. So here is the elite weight percentage produced as a function of 2 years, right? And you can see it's a fairly Gaussian distribution. So what we did was we took all of this data and all the process parameters, which is around 70 process parameters, and then tried to predict A-light, B-light and ferrite phases. And we did this with different combinations. Okay, what are the different combinations we considered? We predicted it only using process parameters. We used it with process parameter and kiln feed, hot meal, process parameter and kiln feed, and with clinker oxide. The bottom line is that we are able to predict all three A-light, B-light and ferrite phases with high accuracy. Actually, we use random forest for this prediction. When you use it as a function of all these input features that I mentioned, and we are also able to predict it accurately, for example, as a time series as well. So this work is already published, and interestingly, this work also got featured by Nature Reviews Clean Technology as part of a research highlight, which also highlights the importance of how such solutions can have an impact on industrial scale as well. So some of the concluding thoughts: AI is going to stay, learn it, and data is the key. Generate it. When you are training an AI model, make sure that you use the right loss function and architecture. This is very important. So don't use AI as a black box. Try to understand what's happening inside and make sure that you use the right model, right architecture and right loss function. Fair data. Make sure that your results are reproducible and share the data. Identify the correct problem. So don't use AI for all the problems. Which part of solution can be replaced by AI in a meaningful fashion? Use AI only there. And then finally improve AI by bringing in ideas from domain towards improving AI. So simply using AI in your domain is not going to help. Unless domain scientists and AI scientists work together, it's not going to be beneficial, and we'll see that AI is not working the way we expected it to work. And there are several examples that I can give you. Maybe during the interaction, if you have any questions, I can talk about that. And before I conclude, I just want to share this book that we have recently published called titled Machine Learning for Materials Discovery, and this gives you a lot of numerical recipes and practical applications on how to use AI in your domain. Thank you, and I hope now the stage is open for questions. Once again, thank you for giving me this opportunity, and I look forward to the interaction.